So today we're going to be talking about lesson 6.1 from your book, Perpendicular and Angle Bisectors. We're going to kind of do a gentle introduction to this lesson, which has a lot of good stuff in it, this chapter, some interesting things happening. But today really just a couple of quick proofs and some reminders of definitions and a few little things going on here. We want to be able to use theorems about perpendicular and angle bisectors. We want to be able to identify perpendicular bisectors and angle bisectors, use those theorems, and write equations of perpendicular bisectors. So a lot of the stuff we've been doing all year long, we're just going to continue today. So one of the big takeaways from this lesson is what happens when we have a perpendicular bisector of a line segment. So I've created this segment for you in GeoGebra, and I'm going to draw its perpendicular bisector. And we remember what perpendicular bisector means. It's a line that's perpendicular to the line segment that also cuts that line segment exactly in half. So GeoGebra allows me to do that pretty easily. I create that segment, and I can see there's a right angle formed there, and I also know that that segment AB is cut exactly in half. And I've added point C on there to demonstrate that's the midpoint of that segment. So one of the takeaways from this lesson is, let's put a point on this perpendicular bisector, and I'm going to connect that point to the ends of the endpoints of that original segment that I created. And as I move that point D, I notice my triangle, the sides of it change as well. I can have GeoGebra find for me the lengths of the sides of that triangle. And I notice something here, that the two sides of that triangle, side AD and side BD, are both 5.1. I wonder if that's going to happen as I move that point D along that perpendicular bisector. And here's what I notice, just numerically. I notice that those two sides are congruent, which means I made an isosceles triangle. What we're trying to show here is our first theorem from the book, which is that in the plane, if a point lies on a perpendicular bisector of a segment, then it is equidistant from the endpoints of that segment, which means that that point D is equidistant from point B and from point A. So what we want to do is, today I'm going to have you prove that as part of your homework. Okay, so given a certain information, we're going to prove that AD is congruent to AB. And it turns out the converse of that perpendicular bisector theorem is also true, that in the plane, if a point is equidistant from the endpoints of a segment, so if, for example, point D is equidistant from A and from B, that's marked by those two lines there, then it lies on the perpendicular bisector of the segment. So CD then must be the perpendicular bisector of segment AB. There's a lot of these little theorems in this unit. Doesn't tell us a whole lot, but the converse also happens to be true. Your book thinks this is a good example of putting this idea to work. The question is there enough information in the diagram to conclude that point N lies on the perpendicular bisector of KM? Well, it looks like what they've told us here is that this is congruent to this, but that's all we know. We do not know that this is a right angle. We do not know that Kn is congruent to Nm. Therefore, no, there's not enough information. Sometimes we have enough information to conclude these things, and sometimes we don't. In this case, that's a no. These examples are taken from page 293 in your book if you want to follow along in the book. And we're using these perpendicular bisector theorems. The first one asks us to find the length of RS. Well, in this diagram, here's what we notice. We notice that RP is bisected by point Q. We have a perpendicular bisector, which means that these two sides should be the same length, which tells me that RS should be 6.8. No big deal there. These are just simple examples of what this means. In part 2, question B, it's looking for the length of EG. Well, we know that these two sides are equidistant, point H is equidistant from the endpoints of segment EG, which means that FH must be a perpendicular bisector. We know it's perpendicular, which means it bisects the length of that segment, which means EF is also 9.5. We're looking for EG, which should be twice that big, which should be 19. And then in this last section, it's asking us to find the length of AD. Well, AD, because we have, again, a perpendicular and a bisector, both perpendicular and bisector, we know those sides are the same, which means that 3x plus 14 should equal 5x. And if I solve for x, x equals 2. I'm looking for the length of ED. 5 times that length of 2 would give us 10. Okay, so just keep those in mind. We basically create isosceles triangles, which give us perpendicular bisectors. Our next theorems talk about angle bisectors, and we have a couple of angle bisector theorems. I've kind of sketched out the idea here in GeoGebra. So what I've got is an angle, and I've constructed the angle bisector. That's the red line, and you notice their measurements are at the vertex of the angle. As I move that angle, you notice that those two things, they're called epsilon and delta. Those two values will remain the same as I move point A or point C around. So we've got an angle bisector. Our angle bisector theorem says that any point that lies on the angle bisector is equidistant from the two sides of the angle. So I've put in the measurements of those segments, segment ED and FD, on the picture here, and we can see as I move those points, those two segments remain the same. We want to remember back that to measure from a point to a line, we have to measure the perpendicular distance, which is why we have that 90-degree angle there. And again, the big takeaway here is that any point that lies on the angle bisector is equidistant from the two sides, which means that this and this are congruent. And I'm also just going to tell you quickly that the converse of that theorem is true as well. And we'll formalize that in the next slide. And an example from your book says a soccer goalie stands in the interior of this angle, which is formed by the path, what does it say? From a BL and BR, the pass from the ball to the goalpost. Why might the goalie want to stand on the bisector? Well, that would be, again, because it's equidistant. It's the same distance to get to that ball no matter where the ball is kicked. Whereas if the goalie were standing over here and the kicker kicks it this way, it's a longer distance out to catch the ball. A slightly more interesting example here would be a question like this that would ask us to find the equation of the perpendicular bisector of the segment with the endpoints at P, negative 2, 3, and Q, 4, 1. So negative 2, 3 would be here, Q, 4, 1 would be here. Here's that segment. What I want to do is find the equation of that perpendicular bisector. Well, the perpendicular bisector should go something like this. I need two things for that perpendicular bisector. I need to know its slope. I also need to know a point that it goes through. And once I get to that point, I can use my y equals m times x minus x1 plus y1. So first thing I need to know is the slope of this original segment. That's up 2 and over 1, 2, 3, 4, 5, 6. Up 2 and over 6 would be a slope of negative 1/3, which means that the line I'm looking for, that perpendicular line, would have a slope of positive 3. And I also need to know the midpoint because this is going through the, this is an angle, segment bisector rather, it's going through the midpoint of that segment. And we remember how to do that. We're going to add the x's, add the y's, and divide by 2. So my midpoint would be, midpoint of PQ would be a coordinate point. I'm going to add the x's, negative 2 and 4 is 2, divided by 2 is 1. Add the y's, 3 plus 1 is 4, divided by 2 is 2. So my midpoint should be at 1, 2, which is pretty close to what I have drawn there. And I'm just going to plug into my formula. Y equals 3 times x minus 1 plus 2. That's y equals 3x minus 3 plus 2, or y equals 3x minus 1, which looks pretty close to what I have drawn there. Okay, so we do a couple of things there. Point slope formula, and we need to know slope, and we need to find the midpoint. And that's it for today's lesson, guys. I'm going to have you do some problems in the book, and we'll talk to you tomorrow. So we'll go into the book, do page 296, 2 through 22 even, and I will post a picture of that work and that page in Schoology for you. So that's it, guys. Take care. Bye-bye.